In the previous video, we went through calculations and numerical problems under the topics of the AC circuits for first year university physics. We also went through questions under the electric field, electric potential, the Coulomb's law, which is F is equal to K Q1 Q2 divided by R squared. We also went through questions under the Gauss law, which basically states that this psi, that is electric flux, is equal to the sum of the charges divided by the permittivity. We also went through questions under capacitance. So if you have not actually gone through that video, I would really recommend that you do that. The link to the video has been dropped in the description section. Now here we're going to take a successive video which actually goes on to deal with questions under first year DC circuits and also electromagnetism. Now this is going to be a little bit broad because under electromagnetism we got the Faraday's laws of electromagnetic induction. We got the questions under the force on two long straight parallel wires carrying currents in the same direction. And we also got questions under what is that going to be now? So we got questions under magnetic fields also. And so this will be a really broad part of this question. So this is the first of the number of questions we're going to try under this. So this is number 10. We actually stopped at number 9 from the previous video. Number 10 says, estimate the drift velocity and the current density in a copper wire of thickness 2 millimeter and radius 1 millimeter carrying a constant current of 5 amps. Now there are about 10 to the power of 29 electrons per unit volume of the copper. So let us say this is the copper section, and this is the length of it. Now the thickness, that is the distance from this point to this point. This is the same thing as the diameter of the circular part. This is going to be a circular face that has a diameter of a 2 millimeter. Now in this case we were given the radius also, which is R, and R is equal to 1 millimeter. Now 1 millimeter is the same thing as 1 multiplied by 10 to the power of a negative 3 in it. So this is going to be 10 to the negative 3 meters. Now we're also given the current, so I'm going to write that there. Current is equal to 5 amps. And V also gave us the number of electrons there, so that is 10 to the power of 29. Now what is the charge of an electron? That is written as a 1.602 multiplied by 10 to the power of 19 Coulomb. Now the current that flows within a section of a conductor as related to the drift velocity of the charges, that is represented by this formula. I is going to be equal to N, A multiplied by EV. Now A stands for the cross-sectional area. E stands for the charge of the electron. V would stand for the velocity. If I took A, which is a cross-sectional area, and divided it through into this equation, I'm going to have I divided by A, and that will be equal to N EV. This stuff is called as the current density, and this is basically represented as a J. So if you got the cross-sectional area as well as the current, you could well find out what is the current density. In other words, you could also use this. That is the number of electrons, the charge of it, as well as the drift velocity. Now, we do not really have the charge density, or in this case, the current density rather. We do not have that, so we just need to find everything one after the other. So before we do that, we need to find out what is the cross-sectional area. And because we got this to be a circular surface, the area of a circle, that is equal to pi r squared. We got r to be 10 to the power of a negative 3. So the area in this case is going to be pi multiplied by 10 to the negative 3. That will be raised to the second power. So this obviously is going to be pi multiplied by 10 to the negative 6 meters squared. So in this case, we're going to have I. So we need to find the drift velocity first of all. So I just need to make that as a subject. V is going to be equal to I. That will be divided by NAE. Basically, that is what we got. Now, what is I? I is 5 amps, so that is going to be 5 amps written there. This will be divided by the number of electrons first. So this is 10 to the power of a 29. This is multiplied by cross-sectional area. So this will be pi multiplied by 10 to the power of a negative 6. Now we need to have that multiplied with the charge of an electron, which is given as a 1.602 multiplied by 10 to the power of a negative 19. So I'm going to take these ones out for now. These ones are going away. So let us get what that is going to give. So that gives us 9.93 multiplied by 10 to the negative 5. So this is going to be 9.93 multiplied by 10 to the negative 5. So this will be meter per second. That is what we got. Now we also need to find out what is the current density. Now as you can see, the current density is represented with this formula. So let us plug that into perspective and find out what that is going to give. So here we're going to have the current density. That will be current divided by the area. Now what is the current? The current was given as a 5. That is 5 amps. And that will be divided by A. A is the cross-sectional area. Now the cross-sectional area has been found as a pi multiplied by 10 to the power of a negative 6. So J in this case, that should be 5 divided by pi multiplied by 10 to the power of a negative 6. So this is going to give us a 1.59 multiplied by 10 to the power of 6. So we got this as current, that is going to be amps. This is area. So this will be per meter squared. This is going to be the answer for the current density. So that is basically it for this question. Now here is the 11th question. If the resistance of a copper wire at ice point is 45 ohms, what is its resistance at 67 degrees Celsius? Now we need to take the temperature coefficient of resistance as alpha. Alpha is equal to 3.93 multiplied by 10 to the negative 3. Now there is a law that relates the temperature coefficient of resistance to the resistance at various temperatures. And that states that the coefficient, which will be represented as a alpha in this case, that is equal to the change in the resistance. So I'm going to write that as a dr. That will be divided by r dt. dr stands for the change in resistance, and dt, that is the change in the temperature. Now change in the resistance, that could be represented as the final resistance divided by the initial resistance. This is the resistance of the wire at the ice point or the 0th temperature, where T is equal to 0 degrees Celsius. Now if you got T equal to 0 degrees Celsius, that should be 273. So I need to change this. This is T is equal to 0 degrees Celsius or 273 Kelvin. Now this is going to be R naught. That is the initial resistance. And dt, that will be T2 minus T1. So this is what is equal to alpha. Now we're going to take this stuff and have it multiplied with the alpha. So that will be alpha R naught. So this is R naught multiplied by T2 minus the T1. And this is equal to R minus R naught. So we're going to take this and basically have it multiplied into everything. So that will be alpha R naught T2. Well, instead of doing that, I'm just going to leave it. So this is what I'm going to do. This stands for the resistance at a temperature. Let us say that is a resistance the resistance at a temperature T. So we want to make this as a subject. So in order to do that, I need to take the negative R naught to this other side. So that is going to be RT. That will be equal to R naught plus a alpha R naught multiplied by T2 minus a T1. So from here, we could well factor R naught out. And so R sub T, that will be equal to R naught multiplied by 1. And as we take R naught and have it divided into this stuff, that is going to take R naught out. So we would be left with this. So here now we should have a T2 minus a T1. So this is what we have. So this will be the formula that we're going to use. Now R naught, that stands for the resistance at 0 degrees Celsius or 273 Kelvin. Now, we were told that the resistance of the copper wire at ice point is 45 ohms. So I'm going to write that there. That will be the resistance. So we're asked to find out what is going to be the resistance at 67 degrees Celsius. Now, this is T2. T1 is 0 degrees Celsius, and that is obviously 273 Kelvin. Now T2, that is 67 degrees Celsius. That will be 67 added to this. So first, that is going to give us a basically 273 added to 67. That will be 0 here. This is a 4 here, and then we're going to have a 340. So this is going to be a 340 Kelvin. Now, because we have this as subtraction, you do not really need to have these converted, but if you want to do that, just go ahead. There ain't no problem about that. Now, alpha was also given to us, isn't it? Alpha, that is 3.93 multiplied by 10 to the power of a negative 3. So let us find what RT is. So RT, that is equal to R naught, which is 45. This will be multiplied by 1 plus alpha. Now, what is alpha? We got that to be 3.93 multiplied by 10 to the power of a negative 3. Now, we need to find the change in the temperature. Changing the temperature, that will be T2 minus a T1. Now, T2, that is 340 Kelvin or 67 degrees Celsius. Now, that will be subtracted with 0 degrees Celsius, which should still give us this in the equivalents. So this is going to be 67. So this is R sub T. So let us see what that is going to give. So that will be 1 plus this is 3.93 multiplied by 10 to the power of a negative 3. This is going to be multiplied by 67. Okay, so I need to add it here. So that gives us 56.848. That will be 56.848. Now that is 84895. Now approximately That is going to give us R sub T equal to 56.85. 56.85 ohms. This is the answer. Number 12. The thickness of a 12-meter long copper wire is 3 millimeter. If this wire carries a drift current of 7 amps, find the resistance, the conductivity, as well as the potential difference in the wire. Now, we were given the resistivity as a rho, that is a 1.7 multiplied by 10 to the negative 8. So first we're going to find the conductivity, that is 1 divided by rho. So this is going to be 1 divided by 1.7 multiplied by 10 to the power of a negative 8. So that gives us 5.88 multiplied by 10 to the power of a 7. So this will be per ohm per meter. That is going to be the answer. Next up, we need to find the resistance. Now, resistance is given as a rho L divided by A. L stands for the length of the wire, and A, that stands for the cross-sectional area. Now, the thickness was given as a 3 millimeter in it. Let us say this is a copper wire, and so you got the thickness here. And so from here to this place represents the thickness, which would give us a diameter. And so radius, of course, is always going to be d divided by 2. So we need to divide this, and that is going to be 3 divided by 2, which gives us 1.5. So I'm going to multiply this by 10 to the negative 3. That changes millimeter to meters. Now the length of the wire was given as a 12 meter long, so that is 12. So R in this case is going to be rho. Now rho was given as a 1.7. That is multiplied by 10 to the negative 8, multiplied by the length, which is 12. And so we got this. That will be divided by the area. Now the area in this case, that will be pi r squared in it. So that will be pi multiplied by 1.5 multiplied by 10 to the negative 3. This will be squared. So I just need to take that and plug it here. So that is going to be 1.5 multiplied by 10 to the negative 3 to the power of a 2. So that is a 1.7 multiplied by 10 to the power of negative 8. So this gives us 0.02886. Now if we got R to be equal to 0.02886, this is going to be the same thing as 2.89 multiplied by 10. So that will be 10 to the power of a negative 2 ohms. This is going to be the resistance. Now we need to find the potential difference, which is in the wire. Now potential difference from the Ohm's law is given as a V is equal to IR. Now the current was given as a 7 amps. That will be multiplied by the resistance. So that is 2.89. That is multiplied by 10 to the power of a negative 2. So what will that give us? So that gives us 0.2023. A draw cell of EMF 1.5 volts and internal resistance 2 ohms is connected to a bulb of resistance 5.5 ohms. Now we need to determine the current in the circuit, the last volt also, as well as the terminal voltage. So let us draw this circuit. So this is basically going to be how the circuit is going to look. So I'm going to rewrite this. Okay. Now this stuff is the external resistance. There is actually an internal resistance. I'm just going to place it here. So we got an EMF which is equal to 1.5 volts. So first, the internal resistance which was given to us here, that is 2 ohms. Now we got the external resistance. There is only one external resistor, so I'm just going to place that as the RT. The voltage that will be wasted over this external resistor, that is what is called as a terminal voltage. Now the voltage wasted over the internal resistor, that will be the last volts. Now RT is given as a 5.5 ohms. Now we got E. That is the EMF of the DC source. That was given as a 1.5 volts. So from the formula of DC circuits, the total or net current within a DC circuit is given as the EMF divided by the total external resistance added to the internal resistance. So that is going to be 1. This is 1.5. This will be divided by RT, which is 5.5, plus the R. R is a 2. So this is 1.5. This is divided by 7.5. This gives us 1 divided by 5, which is basically going to end up with a 0.2 amps. So in this case, we got the net current within this DC circuit. Net current, that is going to be 0.2 amps. Now we need to find out what is going to be the last volt. Now the last volt, that is basically represented as a, well, I'm just going to represent that as a V sub L. And that is given as the net current, or IT. Just going to represent it as a INET for now. That will be multiplied by R. So V sub L is going to be 0.2 multiplied by 2, which is going to give us a 0.4 volts. So VL is going to be equal to 0.4 volts. This is the last volt. Now, what is the last volt? The last volt is the potential difference which is actually dissipated on the internal resistance. So even though we got 1.5 volts as a rating of the EMF source, that is not completely all that will be available for this DC circuit. In this case, we already got 0.4 volts, which has dropped away from the total. So what should be left should be 1.1 volts. Now, if you want to calculate it, you could go ahead, but subtracting this, the last volt from the total DC source EMF, that is going to give you 1.1 already. Now, the formula for terminal PD, or terminal voltage, that is represented as the total current multiplied by the total resistance. So I'm going to write that as a VT. Now, total current, that will be 0.2. We already found that. And R sub T, that is going to be 5.5. And so this gives us 1.1, as we already determined. Number 14. 5 40 ohms bulbs, 3 15 ohms torchlights, and 7 9 ohms fuses are connected to a 240 line for, well, this is 240 volts. This is the EMF source for the DC circuit. Now these were connected for 3 days. So first we need to find out the net current which is drawn during this period, but also to find out what is going to be the power. We also need to find out what will be the cost for the energy being kept on for so long. Now 1 kilowatt hour of energy costs 15 hours. So we're going to use that later on. So first we got a 40 ohm bulb which is here. So the resistance of the bulb is given as a 40 ohms. Now we got 5 of them. So that is going to be 5 of the bulbs. So that is going to be 5 multiplied by 40. That should give you 200. Next up, we got the torch lights. So that is going to be the resistance of the torch lights, which is 15 ohms. Now, we got 3 of them. So that is going to be 3 RB. That will be 3 multiplied by 15, which is going to give us a 45. Next up, we got the resistance of the fuses. I'm going to represent that as a R sub F. Now, the resistance of one fuse is 9 ohms. We got 7 of them, so that is going to be 7 RF. And this is going to be 7 multiplied by 9. That will give us 63 ohms in it. So we need to find out what is going to be the total of resistance. Bear in mind, you got these appliances connected in series. So their resistances are going to be added thus. 200 plus 45 plus the 63. So that gives us 308 ohms. I'm going to write that here. The total resistance is 308 ohms. Now, we need to find the current which is drawn during this period. Now, we got the EMF, which is the total voltage provided for the connection. That was given to us as 240 volts. Now, we know that the total voltage is given as the total current multiplied by the total resistance. So we need to find this. So R sub T, that will be V sub T divided by R sub T. So that is going to be 240 minus 308. That gives us point. So we're going to have a 0.779 amps. Now we need to find out what is going to be the power delivered. Now you could find power using this formula. P is equal to IV. We already know that I, well V rather, is the same thing as a I multiplied by R. So this could also be represented as a I squared R. Now R stands for the total resistance of the complete connection. So instead of going so far, I'm just going to use these ones. So the current has been found to be 0.779. That will be multiplied by V. V was given as a 240. So the power in this case is going to be 187.01. So I'm just going to leave it that way. This is 187 watts. Now we need to find out what is going to be the cost for keeping the appliances on for so long. Now first, we got 1 kilowatt hour. That costs 50 naira. Now what is 1 kilowatt hour? Power is given as work divided by time. Now the unit of power, that is watts, and the unit of work, that is joules. The unit for time, that is seconds. Let us say in this case we represent that as a hour. So if I took this and multiplied it with this, I'm going to have watt hour will be equal to joules. I could change this to kilowatts, but you just need to know that this is the same thing as a power. If you got power in watts, that is the same thing as having it in kilowatts. Just that in this case, you need to multiply with 10 to the power of 3. And then multiply by whichever value you're going to have there. So you could express it basically in whichever multiple or prefix that you choose. So as you can see, this is the representation for energy. You could have kilowatts hour. Now, what is going to be 1 kilowatt hour? So I'm going to take these out now. 1 kilowatt hour, that is equal to 3.6 multiplied by 10 to the power of 6 joules. This is what it is. So what I'm going to do is change the power which we got and the time. Apply them in seconds. So doing that will change it directly to joules. We know that power is equal to work divided by time in it. Now the power was gotten here to be 187. Now we got the work, that is divided by time. Time was given as in 3 days. Now 3, that is going to be multiplied by 24 hours. Now 1 hour carries 60 minutes. In every minute, there is going to be 60 seconds. So let us see what that is going to give. We got 3 multiplied by 24 multiplied by 60 with another 60. So in this case, I'm going to see that 187, that is equal to the work done divided by 25, 200. So we need to multiply this together to find out what will be the work done. So work done, which in this case will be directly in joules, that is 187 multiplied by 259,200. So that is going to give us W is equal to 484,70400. Now I'm going to express this in standard form. So this is going to be equal to, let us try to find out what that is going to be. This is 1, 2, 3, 4, 5, 6, 7. So that is going to be 7. So here we got 4.85 approximately multiplied by 10 to the 7th joules. Now you can use this to find out what is going to be the equivalent in kilowatt hour, but we do not really need that. So what we know here is that 1 kilowatt hour, which is also given as a 3.6 multiplied by 10 to the power of 6 joule, that is equal to 15 hour. So what we need to find out is the amount that will cost to keep it at 4.85 multiplied by 10 to the power of 7. What is this going to give? So I'm just going to cross multiply. I'll take this and have it multiply with this. And I'm going to do the same thing on these other side. So that is 3.6 multiplied by 10 to the power of 6 multiplied by x. And on this side, we're going to have a 50. That will be multiplied by 4.85 multiplied by 10 to the power of a 7. Now x is going to be equal to 50, that is 50 naira, multiplied by 4.85, multiplied by 10 to the 7th. Now this is joules in it, so I'm just going to express that there. And this will be divided by 3.6 multiplied by 10 to the power of a 6 joules. From here, obviously, you can see that the joule cancels out. And so let us see what this is going to produce. What will be the final answer? So that gives us 673.611. So the amount that will cost is 673.611. So this is the amount in naira. So in order to keep these appliances on for 3 days, you need to pay 673.611. Question 15. 4 resistors, 4 ohms, 7 ohms, 2 ohms, and 5 ohms are connected in parallel in a DC circuit. Now a net current of 2.5 amps is released by this circuit. So the first question we're required to find, to answer, is to find the effective resistance in the circuit. So this is what I'm going to do. I'm just going to write out the expression for it, or draw out rather. So this is going to be the diagram for it. So this will be the first resistance. This is going to be the second. This will be the third. And this is going to be the last, which is the fourth. So this is going to be R1. This is R2. This is going to be R3. And this is R4. Now the EMF, I'm just going to write that as an E. So we have the net current passing through it. Because we got this as the EMF source, and this is a positive terminal, we're going to have that current. Current will move in its direction, and that is going to end in its direction. So in that case, we're going to have current move in this direction. So this is the total current. Now the total current will be dissipated over this, and over this, as well as over this. And we need to, first of all, find the effective resistance. Now, for parallel connection of resistors, there is actually a basic number of ways that you could use to find the effective resistance or the total resistance within that circuit. And the most recommended way is actually to use this way. That will be 1 divided by R1 plus 1 over 4, or 1 over 2 plus 1 over 3. This will be 1 over R4. So this is R3. And this is going to be raised to the power of a negative 1. So here we got 1 divided by R1. Now let us say R1 is a 4. Now R2, that is a 7. R3, that is a 2. And R4, that is a 5. So this is going to be raised to the power of a negative 1. So that gives us 0.915 or 0.92. So the effective resistance here is 0.92 ohms. That is going to be the answer. So R effective, that is going to be equal to 0.92 ohms. Now the net current, which is given as a IT, that is equal to 2.5 amps. So we are required to find out what is going to be the current passing through each resistor. Now how can you find that? How can you find the current passing through each resistor? Now there is basically two formulas that you could use to find out how that is going to be. The first formula is by the normal methods. So we know that the EMF, which was given, that is going to be equal to R EFF multiplied by IT. That is the EMF of the DC source. So we got our effective, that is 0.92. And this is going to be multiplied by 2.5. So that gives us 2.287, which in this case, I'm just going to approximate that. That is 2.29 volts. Now, what this means is we got 2.29 as the voltage or the EMF of the DC source. Now, you need to remember that in parallel connections, the same voltage is basically going to be wasted over each resistor. So for the first resistance, I'm going to call that as a R1. But the voltage which will be wasted over this, that is called as a V1. Now V1 is going to be equal to V2. That will be equal to V3. And that is equal to V4. And that is going to be totally the EMF or the voltage of the DC source. So let us find out V1. V1 is going to be I. So that should be I1 multiplied by R1. Now we know V1. V1 is the same thing as E. That is 2.29. We know R1. And R1, that is that was given as a 4 ohms. So R1, well, that should be I1 rather. That is equal to V1 divided by R1. So V1, that is 2.29. This will be divided by R1, which is a 4. So that gives us 0.5725. Now from here, we can find out what is going to be the second. So I2, that should be equal to V divided by R2. So V, that is 2.29. That should be divided by R2, which is given as a 7. So that gives us 0.3271. So I2, that is 0.3271 amps. Now how about I3? Now I3 is going to be V divided by R3. So that is 2.29 divided by R3, which is a 2. So in that case, we got 1.145. That is I3. 1.145 amps. Now finally, we need to find I4. That is going to be V divided by R4. So that is 2.29 divided by 5. This gives us 0.458. So that will be, well, I think I'm going to write it here. I4 is equal to 0.458 amps. Now we're going to test all these values. If we add these values together, are they going to give us this, the total resistance? Because for parallel connection, IT is going to be equal to I1 plus I2 plus I3 plus I4. Now we already got the total current as a 2.5. So we need to add these individual currents to find out whether or not that is going to give us a 2.5. Now I1 is a 0.5725. And we need to add that to I2. That is 0.3271. I3 is 1.145. And we got I4, which is a 0.458. Now this gives us 2. So I'm going to take these out. This is equal to 2.5026 amps, which could be approximated to 2.5, which is what we also have here. The current there was at 2.5. So this is actually correct. We're on track. Now finally, we need to find the EMF of the DC source. Well, the EMF of the DC source has already been given. That is exactly what I took out. So basically, we've answered every question from here. A 5.0 mega ohms resistor is connected to a 2 microfarad capacitor in series with an EMF source of 60 volts. Well, that is a 6.0 rather. So after 5 seconds of connection, we need to determine the charge on the capacitor as well as the charging current. And we also need to find out what is going to be the time constant. Now this question basically comes from the RC circuits under DC circuit, where you have a resistor and the capacitor connected in a DC circuit. When you do that, there is always going to be some amount of the charging current which will be accumulated on the capacitor. And there will be some charges on the capacitor. So first we got the resistance. The resistance, that is 5.0 mega ohms. Now we're going to rewrite this. So we're going to have a 5.0 multiplied by 10 to the power of 6. This is the value of mega. So this is 5.0 times 10 to the power of 6 ohms. We got the capacitance, that is 2 microfarads. This is equal to 2 multiplied by 10 to the power of a negative 6 farads. And we got the EMF source. I'm going to write that as an E, and that is 6.0 volts. And we also got time. Time is equal to 5 seconds. Now, this follows a formula of charge, Q, to be equal to E multiplied by C. This is equal to, well, open bracket rather, 1 minus E. This is E raised to the power of minus T divided by RC. This is the formula you need to use. Now, E stands for the EMF. C, that stands for the capacitance. And T stands for the time. R, that stands for the resistance, while C, again, that is the capacitance. So let us see what that is going to give. So we got the charge, that is equal to E. Now what is E? In this case, E is a 6.0. This has got to be multiplied by C, which is this stuff. So that is going to be 2 multiplied by 10 to the power of a negative 6. This is going to be multiplied by 1. That will be minus E. E raised to the power of a minus T. Time is 5 seconds. This is going to be divided by RC. Now what is RC? RC is 5.0 multiplied by 10 to the power of a 6, and that will be multiplied by 2 multiplied by 10 to the negative 6 in it. Well, so that should be 10 to the power of a negative 6. Now this stuff, they're basically going to cancel out. So we should have 5 multiplied by 2, which gives us a 10. So in that case, I'm going to rewrite this. This is just 5 divided by 10. And that gives us 4.72 multiplied by 10 to the negative 6. So that will be 4.72 multiplied by 10 to the negative 6 Coulomb. Now this could also be rewritten as a 4.72 microfarads. Well, microcoulomb rather. Next up, we need to find out what is going to be the charging current. So I think I'm going to wipe these out. Now the charging current is given as a I, and that is equal to E. That is E divided by R, and that will be multiplied by E to the power of a negative T over RC. So E, that is 6.0, R, that is 5.0 multiplied by 10 to the power of a 6. This is going to be multiplied by E. That will be to the power of a negative T, which is 5 seconds. This is going to be divided by RC, which is still a 10. So that is going to give us 7.27, which I'm just going to approximate that. So that will be 7.28. And that will be multiplied by 10 to the negative 7 amps. This is the charging current. Next up, we need to find the time constant. How can you find the time constant? Now the time constant is equal to RC. So that will be T, and that is equal to RC. So we got R. R, that is, that should be 5.0 multiplied by 10 to the power of 6 multiplied by C, which is 2 multiplied by 10 to the negative 6. So as this cancel out, the time constant here basically is going to be equal to 10 seconds. So that will be the answer for that one.